Welcome to this course about tools for data science. This course is designed for all learners who want to become data scientists. As a data scientist, you will be working with data, and this course will provide you with knowledge about various tools that you can use to analyze and derive conclusions. You can go through this course with or without programming knowledge. Now, a data scientist's toolkit consists of many tools, and in this course, you will explore a variety of them in the following modules. Module 1, Overview of Data Science Tools. Module 2, Languages of Data Science. Module 3, Libraries, APIs, Datasets, and Models. Module 4, Jupyter Project. Module 5, RStudio and GitHub. Module 6, Final Project, Create a Jupyter Notebook. And Module 7, an optional module, IBM Tools for Data Science. Let's now get some insight into what each module offers. In Module 1, you will learn about the different categories of data science tools and examples of open source and commercial offerings in each category. In addition, you will learn how the tools overlap in functionality and what their pros and cons are. Module 2 will give you an overview of the commonly used languages that are available in data science, like Python, R, Scala, Java, Julia, and SQL, and what they are used for. In the third module, you will learn about libraries that contain built-in modules providing different functionalities. You will also learn that an application programming interface, or API, allows communication between two pieces of software. Further, in the module, you will explore open datasets on the Data Asset Exchange, or DAX. And finally, you will learn how machine learning, or ML, uses algorithms, also known as models, to identify patterns in the data. In Module 4, you will learn about Project Jupyter, one of the most commonly used environments among data scientists. You will explore the three main applications of Project Jupyter, Jupyter Notebook, Jupyter Lab, and Jupyter Lite. In addition, you will be introduced to commercial Jupyter-based applications such as IBM Watson Studio and Google Colab. And this module also gives an overview of Jupyter distributions that can be installed on your own system, like Anaconda. Module 5 will start with an introduction to R and RStudio. You will learn about the different R visualization packages and how to create visual charts using the plot function. In addition, you will learn about GitHub, a popular version control platform that data scientists can use for sharing their projects and showcasing their portfolios. In Module 6, you will work on your final project, in which you will create and share your Jupyter Notebook. You will submit your project and also grade your peers. Finally, Module 7 is an optional module that gives an insight into additional IBM tools, like Watson Studio and IBM Cloud Pak for Data as a Service, that includes IBM Watson Knowledge Catalog, IBM Watson Machine Learning, and more. So there's a lot to cover here. To get the most from this course, complete viewing each video, complete all hands-on labs, and check your learning with each quiz. We are very happy to have you with us as you start your Tools for Data Science journey. And if you have any trouble with any of the course material, please don't hesitate to contact us in the discussion forum. So let's get started, and good luck! Welcome to Categories of Data Science Tools. After watching this video, you will be able to list the tasks that a data scientist needs to perform, show how code asset management and data asset management help build models, and describe how execution and development environments implement a model. Before it can be useful, raw data must pass through various data science task categories such as data management, data integration and transformation, data visualization, model building, model deployment, and model monitoring and assessment. To do these tasks, you need data asset management, code asset management, execution environments, and development environments. Let's see how each category enables you to make the best use of raw data. Data management is the process of collecting, persisting, and retrieving data securely, efficiently, and cost-effectively. Data is collected from many sources like Twitter, Flipkart, media, sensors, and more. Store collected data in persistent storage so it is available whenever you need it. Data integration and transformation is the process of extracting, transforming, and loading data, and this is called ETL. Some of this data is distributed in multiple repositories, for example, a database, a data cube, and flat files. Use the extraction process to extract data from these numerous repositories and save to a central repository like a data warehouse. Data warehouses are primarily used to collect and store massive amounts of data for data analysis. Next, data transformation is the process of transforming the values, structure, and format of data. After extracting the data, the next step is to transform the data. In this example, height and weight data needs to be transformed to metric. And once the data is transformed, it's time to load the data. Transformed data is loaded back to the data warehouse. Data visualization is the graphical representation of data and information. You can use visualization to represent data in the form of charts, plots, maps, animations, etc. And data visualization conveys data more effectively for decision makers. It is a crucial step in the data science process. Various forms of data visualizations include a bar chart, which compares the size of each component, a tree map, which displays hierarchy data, a line chart, which plots a series of data points over time, and a map chart, which displays data by location. Map charts can also be applied to other locations, like websites. Now, model building is the next step. This is where you train the data and analyze patterns with machine learning algorithms. The system learns how to provide predictions or decisions by itself. You can then use this model to make predictions on new unseen data. Model building can be done using a service called IBM Watson Machine Learning. It provides a full range of tools and services for building models. The next step is model deployment, the process of integrating a developed model into a production environment. In model deployment, a machine learning model is made available to third-party applications via APIs. Business users can access and interact with the data through these third-party applications, and this helps them make data-based decisions. As an example, the SPSS collaboration and deployment services can be used to deploy any type of asset created by the SPSS software tools suite. Now, model monitoring and assessment run continuous quality checks to ensure a model's accuracy, fairness, and robustness. Model monitoring uses tools like Fiddler to track the performance of deployed models in a production environment. Model assessment uses evaluation metrics like the F1 score, true positive rate, or the sum of squared error to understand a model's performance. A well-known example is the IBM Watson Open Scale, which continuously monitors deployed machine learning and deep learning models. It will improve the accuracy and quality of your predictions. So now that we've reviewed the data science task categories, let's look at some of the tools that support them. Code Asset Management provides a unified view where you manage an inventory of assets. When you want to develop a model, you may need to update it, fix bugs, or improve code features incrementally. All of this requires version control. Developers use versioning to track and manage changes to a software project's code. And when working on a model, teams use a centralized repository where everyone can upload, edit, and manage the code files simultaneously. Collaboration allows diverse people to share and update the same project together. GitHub is a good example of a code asset management platform. It is web-based and provides sharing, collaboration, and access control features. So, as a data scientist, you want to properly store and organize all your images, videos, text, and other data in a central location. You also want control over who can access, edit, and manage your data. Data Asset Management, also called Digital Asset Management, or DAM, is the organizing and managing of important data collected from different sources. DAM is performed on a DAM platform that allows versioning and collaboration. DAM platforms also support replication, backup, and access right management for the stored data. Development environments, also called Integrated Development Environments or IDEs, provide a workspace and tools to develop, implement, execute, test, and deploy source code. IDEs like IBM Watson Studio provide testing and simulation tools to emulate the real world, so you can see how your code will behave after it is deployed. An execution environment has libraries to compile the source code and system resources that execute and verify the code. Cloud-based execution environments are not tied to any specific hardware or software and offer tools like IBM Watson Studio for data pre-processing, model training, and deployment. And finally, fully integrated visual tools like IBM Watson Studio and IBM Cognos Dashboard Embedded cover all the previous tooling components and can be used to develop deep learning and machine learning models. In this video, you learned that the data science task categories are data management, data integration and transformation, data visualization, model building, model deployment, and model monitoring and assessment. And data science tasks are supported by data asset management, code asset management, execution environments, and development environments. Welcome to Open Source Tools for Data Science Part 1. After watching this video, you will be able to list the open source data management tools, list the open source data integration and transformation tools, list the data visualization tools, list the model tools for building, deployment, monitoring, and assessment, and list tools for code and data asset management. So, the most widely used open source data management tools are relational databases like MySQL and PostgreSQL. Also, there are no SQL databases like MongoDB, Apache CouchDB, and Apache Cassandra. In addition, there are file-based tools like Hadoop file system or cloud file systems like Ceph. You also have an Elasticsearch tool that stores text data, including the creation of a search index for fast document retrieval. Now, the task of data integration and transformation in the classic data warehousing world is to extract, transform, and load, or ETL. Data scientists often propose extract, load, transform, or ELT, as data is dumped somewhere and the data engineer or data scientist handles the transformation of the data. Another term for this process emerged: data refinery and cleansing. The most widely used open source data integration and transformation tools are the following: Apache Airflow, which was created by Airbnb originally; Kubeflow, which allows the execution of data science pipelines on top of Kubernetes; Apache Kafka, which originated from LinkedIn; Apache NiFi, which delivers a very nice visual editor; Apache Spark SQL lets you use ANSI SQL and scales up to compute clusters of thousands of nodes; and Node-RED also brings a visual editor. In addition, Node-RED is so low in resource consumption that it even runs on tiny devices like a Raspberry Pi. Now, let's discuss the most widely used open source data visualization tools. You must distinguish between programming libraries where you must use code or tools containing a user interface. PixieDust is also a library but has a user interface that facilitates plotting in Python. A similar approach uses Hue, which can create visualizations from SQL queries, whereas Kibana, a data exploration and visualization web application, is limited to Elasticsearch, or data provider. And finally, Apache Superset is a data exploration and visualization web application. Model deployment is a crucial step. Once you've created a machine learning model capable of predicting some critical aspects of the future, you should make it consumable by other developers and turn it into an API. Apache Prediction I/O currently only supports Apache Spark ML models for deployment, but support for all libraries is on the roadmap. Seldon is an interesting product since it supports nearly every framework including TensorFlow, Apache Spark ML, R, and scikit-learn. Interestingly, it can run on top of Kubernetes and Red Hat OpenShift. Another way to deploy Spark ML models is mleap. And finally, TensorFlow can serve any TensorFlow model using the TensorFlow service. It can be an embedded device like a Raspberry Pi or smartphone using TensorFlow Lite and deployed to a web browser using TensorFlow.js. Model monitoring is an important step as well. Once you have deployed a machine learning model, you want to track its prediction performance while new data arrives to maintain outdated models. Some examples are the following. ModelDB is a machine model metadatabase where information about the models is stored and queried. It natively supports Apache Spark ML pipelines and scikit-learn. A generic multipurpose tool called Prometheus is widely used as well. Although it is not specifically made for machine learning model monitoring, it is used for this purpose. Model performance is measured by more than accuracy. Model bias against protected groups like gender or race is important as well. The IBM AI Fairness 360 open source toolkit detects and mitigates bias in machine learning models. These models, especially neural network-based deep learning models, can be subject to adversarial attacks where an attacker tries to mislead the model with manipulated data or by controlling it. The IBM Adversarial Robustness 360 toolbox detects vulnerability against adversarial attacks and leverages the model to be more robust. Finally, machine learning modes are often considered as a black box applying some magic. The IBM AI Explainability 360 toolkit addresses that problem by finding similar examples in a dataset to be presented to an end user for manual comparison. IBM AI Explainability 360 toolkit can also address the training of a simpler machine learning model to explain the responsibility of different input variables directed toward the final decision of the model. So the choice of code asset management tools has become quite simple. Git is now the de facto standard for code asset management, also known as version management or version control. Around Git emerged several services. The most prominent is GitHub, but the runner-up is GitLab, with the advantage that the platform is entirely open source and can be hosted and managed on your own. Another choice is Bitbucket. Data asset management, also known as data governance or data lineage, is a crucial part of enterprise-grade data science. Data has to be versioned and annotated with metadata. Apache Atlas is such a tool supporting this task. Another interesting project is ODPI Ageria, managed through the Linux Foundation. It is an open ecosystem offering a set of open APIs, types, and interchange protocols that metadata repositories use to share and exchange data. And finally, Kylo is an open-source data management software platform with extensive support for data asset management tasks. In this video, you learned that data management tools are MySQL, PostgreSQL, MongoDB, Apache CouchDB, Apache Cassandra, Hadoop File System, Ceph, and Elasticsearch. Data integration and transformation tools are Apache Airflow, Kubeflow, Apache Kafka, Apache NiFi, Apache Spark SQL, and Node-RED. Data visualization tools are Pixie Dust, Q, Kibana, and Apache Superset. Model deployment tools are Apache Prediction.io, Seldon, Kubernetes, Red Hat OpenShift, mleap, TensorFlow Service, TensorFlow Lite, and TensorFlow.js. Model monitoring tools are ModelDB, Prometheus, IBM AI Fairness 360, IBM Adversarial Robustness 360 Toolbox, and IBM AI Explainability 360. Code asset management tools are Git, GitHub, GitLab, and Bitbucket. And finally, data asset management tools are Apache Atlas, ODPI Ageria, and Kylo. Welcome to Open Source Tools for Data Science Part 2. After watching this video, you will be able to Compare and contrast different open source tools, and describe the relevant features of open source tools. Currently, the most famous development environment data scientists are using is Jupyter, which emerged as a tool for interactive Python programming. Jupyter now supports more than 100 different programming languages through kernels. This encapsulates the execution environment for different programming languages. A key property of Jupyter Notebooks is to unify documentation, code, output from code, shell commands, and visualizations in a single document. Jupyter Lab is the next version of Jupyter Notebooks, and in the long term will replace Jupyter Notebooks. The abundance of architectural changes makes Jupyter more modern and modular. From a user's perspective, the main difference between Jupyter Lab and Jupyter Notebooks is the ability to open different types of files, including Jupyter Notebooks, data, and terminals, and then arrange them on the canvas. Although it has been re-implemented from scratch, Apache Zeppelin was inspired by Jupyter Notebooks and provides a similar experience. Though one key differentiator is the integrated plotting capability. In Jupyter Notebooks, you are required to use external libraries in Zeppelin, and plotting doesn't require coding. You can also extend the capabilities by using additional libraries. RStudio is among the oldest development environments for statistics and data science. RStudio has its origins in the year 2011. It exclusively runs R and all its associated R libraries. In the R environment, Python development is possible. R is tightly integrated into the Jupyter tool and provides optimal user experience. RStudio unifies programming, execution, debugging, remote data access, data exploration, and visualization into one tool. Finally, Spider tries to mimic the behavior of RStudio to bring its functionality to the Python world. And although not on par with the functionality of RStudio, data scientists consider it as an alternative. In the Python world, Jupyter is used more. Now, this diagram shows that Spider integrates code, documentation, and visualizations, among others, into a single canvas. Sometimes your data doesn't fit into a single computer's storage or main memory capacity. Therefore, cluster execution environments exist. The extensively famous Apache Spark is among the most active Apache projects that are used across all industries, including many Fortune 500 companies. The key property of Apache Spark is linear scalability. This means that if you double the number of servers in a cluster, you roughly double its performance. Apache Flink was developed after Apache Spark continued to gain market share. The key difference between Apache Spark and Apache Flink is that Apache Spark is a batch data processing engine capable of processing vast amounts of data one by one or file by file, whereas Apache Flink is a stream processing image with its main focus on processing real-time data streams. And although both engines support both data processing paradigms at the same time, Apache Spark is the choice for most use cases. After Apache Spark and Apache Flink, Ray is one of the latest developments in the data science execution environments and has a clear focus on large-scale deep learning model training. Let's look at open source tools for data scientists, which are fully integrated and visual. This means no programming knowledge is necessary. The tools support a subset of important tasks that include data integration and transformation, data visualization, and model building. Now, Neem originated from the University of Constance in 2004. As you can see, Neem has a visual user interface with drag and drop capabilities. It has built-in visualization capabilities. In addition, it can be extended by programming in R and Python and even has connectors to Apache Spark. Orange is another representative of this group of tools. It is less flexible than Neem, but is easier to use. In this video, you have learned about the most common tasks in data science and which open source tools are relevant. Welcome to Commercial Tools for Data Science. After watching this video, you will be able to list the commercial data management tools, list the commercial data integration and transformation tools, list the data visualization tools, list the model tools for building, deployment, monitoring, and assessment, and list tools for code assessment management, data asset management, development environment, and fully integrated visual. Let's revisit the overview of different tool categories. In data management, most of the enterprise's relevant data is stored in an Oracle database, in Microsoft SQL Server, or an IBM DB2. Although open source databases are coming to the forefront, these three data management products are considered industry standard and will be around for a while. In addition, it's not only about functionality. Since data is the heart of every organization, commercial support availability plays a major role. Commercial supports are delivered directly from software vendors, influential partners, and support networks. Let's start with commercial data integration tools that comprise extract, transform, and load, or ETL tools. According to a Gartner Magic Quadrant, Informatica PowerCenter and IBM InfoSphere DataStage are the leaders. These are followed by SAP, Oracle, SAS, Talend, and Microsoft products. These tools support the design and deployment of ETL data processing pipelines through a graphical interface. They bring along connectors to most of the commercial and open source target information systems. Finally, Watson Studio Desktop includes a component called Data Refinery, which enables definition and execution of data integration processes in a spreadsheet style. In the commercial environment, data visualizations use business intelligence or BI tools. The focus of these tools is to create visual reports and live dashboards. The most prominent commercial representatives are Tableau, Microsoft Power BI, and IBM Cognos Analytics. Another type of visualization targets data scientists rather than end users. For example, the visualization can show relationships between different columns in a table. This functionality is contained in Watson Studio Desktop. If you want to build a machine learning model with a commercial tool, you should use a data mining product. The most prominent products in that space are SPSS Modeler and SAS Enterprise Miner. In addition, SPSS Modeler is also available in Watson Studio Desktop based on the tool's cloud version. Now, model deployment in commercial software is tightly integrated into the model building process. Here is an example of the SPSS collaboration and deployment services, which is used to deploy any type of asset created by the SPSS software tools suite. And the same holds for other vendors. Also, commercial software can export models in an open format. For example, SPSS Modeler supports exporting models as Predictive Model Markup Language, or PMML, which an abundance of other commercial and open software packages can read. Model monitoring is a very new discipline, and currently, relevant commercial tools are not available. Therefore, open source is the first choice. The same is true for code asset management. Open source with Git and GitHub is the de facto standard. Data asset management, often called data governance or data lineage, is a crucial part of enterprise-grade data science. Data must be versioned and annotated with metadata. Vendors, including Informatica Enterprise Data Governance and IBM, provides tools for these specific tasks. The Information Governance Catalog covers functions like a data dictionary, which facilitates the discovery of data assets. Each data asset is assigned to a data steward or the data owner. The data owner is responsible for that data asset and can be contacted. Then, data lineage is covered, allowing tracking back the transformation steps in creating the data assets. The data lineage also includes a reference to the actual source data. And rules and policies can be added to reflect complex regulatory and business requirements for data privacy and retention. Watson Studio is a fully integrated development environment for data scientists. Most people consume it through the cloud. And there is also a desktop version available. Watson Studio Desktop combines Jupyter notebooks with graphical tools to maximize the performance of data scientists. Watson Studio, together with Watson OpenScale, is a fully integrated tool covering the data science lifecycle involving all tasks discussed previously. They can be deployed in a local data center on top of Kubernetes or Red Hat OpenShift. And another example of a fully integrated commercial tool is H2O Driverless AI, which covers the complete data science lifecycle. In this video, you learned that commercial tools support the most common tasks in data science. Data management tools are Oracle Database, Microsoft SQL Server, and IBM DB2. Data integration tools are mainly provided by Informatica PowerCenter and IBM InfoSphere DataStage. These are followed by products from SAP, Oracle, SAS, Talend, Microsoft, and Watson Studio Desktop. Model building tools are SPSS Modeler and SAS Enterprise Miner. SPSS Modeler is also available in Watson Studio Desktop. Informatica and IBM provide data asset management tools. And finally, Watson Studio, together with Watson OpenScale, is a fully integrated tool covering the data science lifecycle. Welcome to Cloud-Based Tools for Data Science. After watching this video, you will be able to describe how commercial cloud tools support data science tasks, and explain how integration provides the ability to use the same tools for multiple tasks. Let's again look at the overview of different tool categories. Since cloud products are a newer species, they follow the trend of having multiple tasks integrated in tools. This integration is applicable for the tasks marked green in the diagram. So let's start with the fully integrated visual tools category. Since these tools introduce a component where large-scale execution of data science workflows happens in compute clusters, we have changed the title and added the word platform. These clusters are composed of multiple server machines transparently for the user in the background. Watson Studio and Watson OpenScale cover the complete development lifecycle for all data science, machine learning, and artificial intelligence or AI tasks. Another example is Microsoft Azure Machine Learning. It is also a full cloud-hosted offering supporting the complete development lifecycle of all data science, machine learning, and AI tasks. And finally, another example is H2O Driverless AI. Although it is a product you download and install, there exists a one-click deployment for the standard cloud service providers. Since the cloud provider does not do operations and maintenance, as with Watson Studio, OpenScale, and Azure Machine Learning, this delivery model should be distinct from platform or software as a service, or PaaS or SaaS. In data management, with some exception, software as a service or SaaS versions of existing open source and commercial tools exist. The cloud provider operates the tool for you in the cloud. For example, the cloud provider operates the product by backing up your data and configuring and installing updates. Some proprietary tools are only available from a single cloud provider. One example of such a service is Amazon Web Services DynamoDB, which is a NoSQL database. It allows storage and retrieving data in a key value or a document store format. The most prominent document data structure is JSON. Now, another flavor of such service is Cloudant, which is a database as a service offering, but in the background, it is based on the open source Apache CouchDB. The advantage is that complex operational tasks like updating, backup, restoring, and scaling are done by the cloud provider. However, the Cloudant service offering is compatible with CouchDB. Therefore, the application migrates to another CouchDB server without making any changes to the application. IBM offers DB2 as a service as well. It is an example of a commercial database made available as a SaaS offering in the cloud, taking away operational tasks from the user. Now let's discuss commercial data integration tools that include extract, transform, and load, or ETL tools, and extract, load, and transform, or ELT tools. It means the transformation steps are not done by a data integration team, but are pushed towards the domain of the data scientist or data engineer. Two commercial data integration tools widely used are Informatica Cloud Data Integration and IBM's Data Refinery. Data Refinery is part of IBM Watson Studio. It allows transforming large amounts of raw data into consumable, quality information in a spreadsheet-like user interface. So the market for cloud data visualization tools is huge, and every major cloud vendor has one. An example of a smaller company offering a cloud-based data visualization tool is DataMeer. IBM offers its famous Cognos Business Intelligence Suite as a cloud solution. IBM Data Refinery also offers data exploration and visualization functionality in Watson Studio. Again, those are examples of a rapidly changing and growing commercial ecosystem among many established and emerging vendors. In Watson Studio, various visualizations depict data for better understanding. An example is this 3D bar chart that visualizes a target value on the vertical dimension that is dependent on two other values in the horizontal dimensions. And you can use colors to visualize the third dimension. Another data visualization is hierarchical edge bundling that depicts correlations and affiliations between entities. If sufficient, a classic bar chart can do the job as well. A 2D scatter plot with a heat map shows two dependent data fields on the y-axis with different color intensities. A tree map shows the distribution of subsets within a set. The famous pie chart does the same but in a non-hierarchical manner. And finally, a word cloud pops out significant terms in a document corpus. Now, model building can be done using a service. One example of a service is Watson Machine Learning. Watson Machine Learning can train and build models using various open-source libraries. Google has a similar service on their cloud called AI Platform Training, and every cloud provider has a solution for this task. Model deployment in commercial software is usually tightly integrated into the model building process. Here is an example of the SPSS collaboration and deployment services, which can be used to deploy any asset created by the SPSS software tool suite. And the same holds true for other vendors. In addition, commercial software can export models in an open format. For example, SPSS Modeler supports exporting models as Predictive Model Markup Language, or PMML, which other commercial and open software packages can read. In addition, Watson Machine Learning deploys a model that makes it available to consumers using a REST interface. Amazon SageMaker Model Monitor is an example of a cloud tool to monitor deployed machine learning and deep learning models continuously. Every major cloud provider has similar tooling. Another tool for model monitoring is Watson OpenScale. Everything marked in green can be done using Watson Studio and OpenScale. In this video, you learned that Watson Studio and Watson OpenScale cover the complete development lifecycle for all data science, machine learning, and AI tasks. In data management, with some exceptions, there exists a software as a service, or SaaS, version of existing open source and commercial tools. Two commercial data integration tools widely used are Informatica Cloud Data Integration and IBM's Data Refinery. An example of a cloud-based data visualization tool is DataMeer and IBM Cognos Business Intelligence Suite. Model building can be done using a service such as Watson Machine Learning. And Amazon SageMaker Model Monitor is an example of a cloud tool to monitor deployed machine learning and deep learning models continuously. Welcome to Languages of Data Science. After watching this video, you will be able to identify the criteria for determining the language to learn, and list the roles involved in data science. For users who are just starting out on their data science journey, the range of available technical options can be overwhelming. There are literally thousands of different programming languages with their own strengths and weaknesses. So, which language should you learn first? The answer to that question depends largely on your needs, the problems you are trying to solve, and who you are solving them for. First and foremost, we recommend considering the Python, R, and SQL languages. However, other languages such as Scala, Java, C++, and Julia with specific features are also popular. And JavaScript, PHP, Go, Ruby, and Visual Basic all have their own unique cases as well. Now, the language you choose to learn will depend on the things you need to accomplish and the problems you need to solve. The problems can be related to the company you work for, what role you have, and the age of your existing application. So, what problems do you need to solve? We'll have a better insight into the answers to this question as we learn more about the popular languages in the data science industry. There are also many roles available for people who are interested in getting involved in data science, and they include business analyst, database engineer, data analyst, data engineer, data scientist, research scientist, software engineer, statistician, product manager, project manager, and so on. In this video, you learned that you should select a language to learn depending on your needs, the problems you are trying to solve, and who you are solving them for. The popular languages are Python, R, SQL, Scala, Java, C++, and Julia. JavaScript, PHP, Go, Ruby, and Visual Basic all have their own unique use cases as well. And the problems you need to solve can be related to your company, role, and the age of the existing application. Welcome to Introduction to Python. After watching this video, you will be able to identify the users of Python, list the benefits of using Python, and describe the diversity and inclusion efforts of the Python community. Python is a powerhouse of a language. It is the most widely used and most popular programming language used in the data science industry. According to the 2019 Kaggle Data Science and Machine Learning Survey, 3/4 of the over 10,000 respondents worldwide reported that they use Python regularly. Glassdoor reported that in 2019, more than 75% of data science positions listed included Python in their job descriptions. When asked which language an aspiring data scientist should learn first, most data scientists say Python. Let's start with the people who use Python. If you already know how to program, then Python is great for you because it uses clear and readable syntax. You can develop the same programs from other languages with lesser code using Python. For beginners, Python is a good language to start with because of the huge global community and wealth of documentation. Several different surveys done in 2019 established that over 80% of data professionals use Python worldwide. Python is useful in many areas, including data science, AI and machine learning, web development, and Internet of Things or IoT devices like the Raspberry Pi. Large organizations that heavily use Python include IBM, Wikipedia, Google, Yahoo, CERN, NASA, Facebook, Amazon, Instagram, Spotify, and Reddit. Python is widely supported by a global community and shepherded by the Python Software Foundation. Python is a high-level, general-purpose programming language that can be applied to many different classes of problems. It has a large, standard library that provides tools suited to many different tasks, including but not limited to databases, automation, web scraping, text processing, image processing, machine learning, and data analytics. For data science, you can use Python's scientific computing libraries like Pandas, NumPy, SciPy, and Matplotlib. For artificial intelligence, it has TensorFlow, PyTorch, Keras, and scikit-learn. Python can also be used for natural language processing, or NLP, using the Natural Language Toolkit, or NLTK. Another great selling point for Python is that the Python community has a well-documented history of paving the way for diversity and inclusion efforts in the tech industry as a whole. The Python language has a code of conduct executed by the Python Software Foundation that seeks to ensure safety and inclusion for all in both online and in-person Python communities. Communities like PyLadies seek to create spaces for people interested in learning Python in safe and inclusive environments. PyLadies is an international mentorship group with a focus on helping more women become active participants and leaders in the Python open source community. In this video, you learned that Python uses clear and readable syntax. Python has a huge global community and a wealth of documentation. For data science, you can use Python's scientific computing libraries like Pandas, NumPy, SciPy, and Matplotlib. Python can also be used for natural language processing, or NLP, using the Natural Language Toolkit, or NLTK. And the Python community has a well-documented history of paving the way for diversity and inclusion efforts in the tech industry as a whole. Welcome to Introduction to R language. After watching this video, you will be able to compare open source with free software, identify the users of the R language, list the benefits of using R, and list the global communities for connecting with other R users. According to the results of the 2019 Kaggle Data Science Survey, which had over 10,000 respondents worldwide, learning 3 languages can earn you an increment, and R offers many possibilities. Now, Python is open source, while R is free software. Let us compare the open source and free software. The similarities are that both are free to use. Both commonly refer to the same set of licenses. For example, many open source projects use the General Public License, or GNU. Both support collaboration, and in many cases, these terms can be used interchangeably, but not all. Now, let's discuss the differences between open source and free software. The Open Source Initiative, or OSI, champions open source, while the Free Software Foundation, or FSF, defines free software. Open source is more business-focused, while free software is more focused on a set of values. So, why R? You should learn R because it is free software. You can use the language in the same way that you contribute to open source. In addition, it allows for private use, commercial use, and public collaboration. R is another language supported by a wide global community of people who want to use the language to solve big problems. Statisticians, mathematicians, and data miners use R to develop statistical software, graphing, and data analysis. R language's array-oriented syntax makes it easier to translate from math to code for learners with no or minimal programming background. According to Kaggle's Data Science and Machine Learning Survey, most programmers learn R after a few years into their data science career, and R is mostly popular in academia. In addition, companies that use R include IBM, Google, Facebook, Microsoft, Bank of America, Ford, TechCrunch, Uber, and Trulia. R has become the world's largest repository of statistical knowledge. As of 2018, R has more than 15,000 publicly released packages, making it possible to conduct complex exploratory data analysis. R integrates well with other computer languages like C++, Java, C, .NET, and Python. Using R, common mathematical operations like matrix multiplication give immediate results. And R has stronger object-oriented programming facilities than most statistical computing languages. Now, there are many ways to connect with other R users around the globe. For connecting to other users, you can use communities such as UseR, YR, SadRDays, and RLadies. And in addition, you can check out the R project website for R conferences and events. In this video, you learned that The Open Source Initiative, or OSI, champions open source, while the Free Software Foundation, or FSF, defines free software. Python is open source and R is free software. R language's array-oriented syntax makes it easier to translate from math to code for learners with no or minimal programming background. And R has become the world's largest repository of statistical knowledge. Welcome to Introduction to SQL. After watching this video, you will be able to explain SQL and relational databases, define the SQL elements, and list the benefits of using SQL. SQL is a bit different than other languages. Officially, it is pronounced as SQL, though some call it SQL. And while the acronym stands for Structured Query Language, many people consider SQL different from other software development languages because it is a non-procedural language. Its scope is limited to querying and managing data. While it is not a data science language, data scientists regularly use it because it is simple and powerful. Some other facts about SQL are that it is older than Python and R by about 20 years. It first appeared in 1974 and was developed at IBM. This language is useful in handling structured data, which is the data incorporating relations among entities and variables. SQL was designed for managing data in relational databases. Here you can see a diagram showing the general structure of a relational database. A relational database is formed by collections of two-dimensional tables, for example, datasets and Excel spreadsheets. Each of these tables is then formed by a fixed number of columns and any possible number of rows. However, although SQL was originally developed for use with relational databases, because of its pervasiveness and ease of use, SQL interfaces have also been developed for many NoSQL and big data repositories. The SQL language is subdivided into several language elements, including clauses, expressions, predicates, queries, and statements. So, what makes SQL great? Knowing SQL will help you get many different jobs in data science, such as a business and data analyst. This knowledge is also a must in data engineering. When performing operations with SQL, the data is accessed directly without needing to copy the data separately, which can considerably speed up workflow executions. SQL behaves like an interpreter between you and the database. SQL is an American National Standards Institute, or ANSI, standard, which means if you learn SQL and use it with one database, you can apply your SQL knowledge to many other databases easily. Now, many different SQL databases are available, including the following: MySQL, IBM DB2, PostgreSQL, Apache Open Office Base, SQLite, Oracle, MariaDB, Microsoft SQL Server, and more. The syntax of the SQL you write may change based on the relational database management system you are using. If you want to learn SQL, you should focus on a specific relational database and then plug into the community for that specific platform. In addition, there are many available great introductory courses on SQL. In this video, you learned that SQL is different from other software development languages because it is a non-procedural language. SQL's scope is limited to querying and managing data. SQL was designed for managing data in relational databases. SQL behaves like an interpreter between you and the database. And if you learn SQL and use it with one database, you can apply your SQL knowledge to many other databases easily. Welcome to Other Languages for Data Science. After watching this video, you will be able to review other languages like Java, Scala, C++, JavaScript, and Julia, and explore how each is used in data science. Previously, we reviewed Python, R, and SQL. In this lesson, we will review some other languages that have compelling use cases for data science. Scala, Java, C++, and Julia are probably the most traditional data science languages. However, JavaScript, PHP, Go, Ruby, Visual Basic, and many others have found their place in the data science community. Let us go through some notable highlights about a few of them. Java is a general-purpose, tried and tested, object-oriented programming language. It has huge adoption in the enterprise space and was designed to be fast and scalable. Java applications are compiled to bytecode and run on the Java Virtual Machine, or JVM. Some notable data science tools built with Java include Weka for data mining, Java ML for machine learning, Apache MLlib, which makes machine learning scalable, and Deep Learning 4 for deep learning. Hadoop is another application of Java, which manages data processing and storage for big data applications running in clustered systems. Scala is a general-purpose programming language that provides support for functional programming and is a strong static-type system. The Scala language was constructed to address the shortcomings of Java. It is also interoperable with Java as it runs on a JVM. The name Scala is a combination of scalable and language. This language is designed to evolve with the requirements of its users. For data science, the most popular program built with Scala is Apache Spark. Spark is a fast and general-purpose cluster computing system that provides APIs which make parallel jobs easy to write. It has an optimized engine that supports general computational graphs. Spark includes Shark, which is a query engine, MLlib for machine learning, GraphX for graph processing, and Spark Streaming. It was designed to be faster than Hadoop. Next, C++ is a general-purpose programming language. It is an extension of the C programming language, or C with classes. C++ improves processing speed, enables system programming, and provides broader control over the software application. Many organizations that use Python or other high-level languages for data analysis and exploratory tasks rely on C++ to develop programs that feed data to customers in real time. For data science, TensorFlow is a popular deep learning library for data flow that was built with C++. And although C++ is the foundation of TensorFlow, it runs on a Python interface, so users don't require the knowledge of C++ to run it. MongoDB is a NoSQL database for big data management that was built with C++. And Caffe is a deep learning algorithm repository built with C++ with Python and MATLAB bindings. A core technology for the World Wide Web, JavaScript is a general-purpose language that extended beyond the browser with the creation of Node.js and other server-side approaches. JavaScript is not related to the Java language. For data science, undoubtedly, TensorFlow.js is the most popular implementation. TensorFlow.js makes machine learning and deep learning possible in Node.js as well as in the browser. TensorFlow.js was also adopted by other open-source libraries including Brain.js and MachineLearn.js. Another implementation of JavaScript for data science is R.js. The project R.js has rewritten linear algebra specifications from the R language into TypeScript. This sets the foundation for future projects to implement more powerful math-based frameworks like NumPy and SciPy of Python. TypeScript is a superset of JavaScript. Finally, Julia was designed at MIT for high-performance numerical analysis and computational science. Julia provides speedy development like Python or R while producing programs that run as fast as C or Fortran programs. It is compiled, which means that Julia code is executed directly on the processor as executable code. It calls C, Go, Java, MATLAB, R, Fortran, and Python libraries and has refined parallelism. Julia as a language is only 8 years old, written in 2012, but there is a lot of promise for its future impact on the data science industry. And one great application of Julia for data science is JuliaDB, which is a package for working with large persistent data sets. In this video, you learned that data science tools built with Java include Weka, Java ML, Apache MLlib, and Deep Learning 4. For data science, a popular program built with Scala is Apache Spark that includes Shark, MLlib, GraphX, and Spark Streaming. For data science, TensorFlow, MongoDB, and Caffe were built with C++. Programs built for data science with JavaScript include TensorFlow.js and R.js. And finally, one great application of Julia for data science is JuliaDB. Welcome to Libraries for Data Science. After watching this video, you will be able to list the scientific computing libraries in Python, list the visualization libraries in Python, list the high-level machine learning and deep learning libraries, and list the libraries used in other languages. In this video, you will review several data science libraries. Libraries are a collection of functions and methods that allow you to perform many actions without writing the code. We will focus on the following Python libraries: scientific computing libraries in Python, visualization libraries in Python, high-level machine learning and deep learning libraries. High-level means you don't have to worry about details, making studying or improving difficult. And finally, deep learning libraries in Python and libraries used in other languages. Now, scientific computing libraries contain built-in modules providing different functionalities, which you can use directly. They are also called frameworks. For example, Pandas offers data structures and tools for effective data cleaning, manipulation, and analysis. It provides tools to work with different types of data. The primary instrument of Pandas is a two-dimensional table consisting of columns and rows called a data frame. Pandas can also provide easy indexing so you can work with your data. NumPy libraries are based on arrays and matrices, allowing you to apply mathematical functions to the arrays. Pandas is built on top of NumPy. You use data visualization methods to communicate with others and display meaningful results of analysis. These libraries enable you to create graphs, charts, and maps. The Matplotlib package is the most well-known library for data visualization. They are popular for making graphs and plots, and the graphs are easily customizable. Another high visualization library is Seaborn. It is based on Matplotlib. This library generates heat maps, time series, and violin plots. Now, for machine learning, the scikit-learn library contains tools for statistical modeling, including regression, classification, clustering, and so on. It is built on NumPy, SciPy, and Matplotlib, and it's simple to get started. In this high-level approach, you define the model and specify the parameter types you want to use. For building deep learning models, Keras allows you to build the standard deep learning model. Like scikit-learn, the high-level interface allows you to build models in a quick and simple manner. It can function using graphics processing units or GPUs, but in many cases, a lower-level environment is necessary for deep learning. TensorFlow is a low-level framework used in the large-scale production of deep learning models. It is designed for production and deployment, but can be unwieldy for experimentation. PyTorch is used for experimentation, making it simple for researchers to test ideas. Apache Spark is a general-purpose cluster computing framework, allowing you to process data using compute clusters. The data is processed in parallel in more than one computer simultaneously. The Spark library has similar functionality to Pandas, NumPy, and scikit-learn. And Apache Spark data processing jobs can be in Python, R, Scala, and SQL. Now, there are many Scala libraries, and Scala is predominantly used in data engineering and data science. Let's discuss some libraries that are complementary to Spark. Vegas is a Scala library for statistical data visualizations. With Vegas, you can work with data files as well as Spark data frames. And for deep learning, you can use BigDL. R has built-in functionality for machine learning and data visualization, but there are also complementary libraries. ggplot2 is a popular library for data visualization in R. You can also use libraries that allow you to interface with Keras and TensorFlow. And R was a de facto standard for open-source data science, but now Python will supersede it. In this video, you learned that libraries usually contain built-in modules providing different functionalities that can be used directly. You can use data visualization methods to communicate with others and display meaningful results of an analysis. For machine learning, the scikit-learn library contains tools for statistical modeling, including regression, classification, clustering, and so on. TensorFlow is a low-level framework used in large-scale production of deep learning models. And Apache Spark is a general-purpose cluster computing framework allowing you to process data using compute clusters. Welcome to Application Program Interfaces, or APIs. After watching this video, you will be able to define an API, list API libraries, and define REST API in relation to request and response. An application programming interface, or API, allows communication between two pieces of software. For example, in a program, you have some data and other software components. You use the API to communicate using inputs and outputs without knowing what happens at the back end. The API only refers to the interface. It is the part of the library you see while it contains all the program components. Now, to further understand how an API works in a library, consider an example of the Pandas library. Pandas is a set of software components where not all components are written in Python. In your program, there is some data and a set of software components. You can use the Pandas API to process the data by communicating with the other software components. The software component at the back end can be the same, but there can be an API for different languages. Consider TensorFlow at the back end, written in C++ that can use APIs for other languages, such as Python, JavaScript, C++, Java, and Go, and thus the API is just the interface. Other volunteer-developed APIs for TensorFlow are Julia, MATLAB, R, Scala, and many more. So REST APIs are another popular type of API. The RE stands for representational, the S stands for state, and the T stands for transfer. They allow you to communicate through the internet and take advantage of resources like storage, data, artificially intelligent algorithms, and much more. In REST API, your program is the client. The API communicates with a web service you can call through the internet. Though there are rules regarding communication, input or request, and output or response. So let's look at some common terms used with regards to API. You or your code are the client. The web service is the resource. The client finds the service via an endpoint, and the client sends requests to the resource and receives a response from the resource. Data is transmitted over the internet using HTTP methods. The REST APIs get all the information from the request sent by the client. The request is sent using an HTTP message that contains a JSON file. The file contains instructions for what operation is to be performed by the web service. This operation is transmitted to the web service via the internet, and the service performs the operation. Similarly, the web service returns a response through an HTTP message where the information is returned using a JSON file, and this information is transmitted back to the client. Now, another example of a REST API is Watson Speech-to-Text API. This API converts speech to text. In the API call, you will send a copy of the audio file to the API. This is called a POST request. Then the API will send the text transcription of what the individual is saying. At the back end, the API is making a GET request. And finally, let's look at our final example, the Watson Language Translator API. You send the text you would like to translate into Watson Language Translator API. The API will translate the text and send the translation back to you. And in this case, the API translates English to Spanish. In this video, you learned an application programming interface, or API, allows communication between two pieces of software. An API is the part of the library you see, while the library contains all the components of the program. And REST APIs allow you to communicate through the internet and take advantage of resources like storage, data, artificially intelligent algorithms, and much more. Welcome to Datasets Powering Data Science. After watching this video, you will be able to define a dataset, describe the types of data ownership, list the sources of data, and describe the Community Data License Agreement. Let's first define what a dataset is. A dataset is a structured collection of data. Data embodies information represented as text, numbers, or media such as images, audio, or video files. A tabular dataset comprises a collection of rows containing columns that store the information. One popular tabular data format is comma-separated values, or CSV. A CSV file is a delimited text file where each line represents a row and a comma separates data values. For example, imagine a dataset of observations from a weather station. Each row represents an observation at a given time, while each column contains information about that observation, such as the temperature, humidity, and other weather conditions. Hierarchical or network data structures are typically used to represent relationships between data. Hierarchical data is organized in a tree-like format, whereas network data is stored as a graph. For example, the connections between people on a social networking website are often represented as a graph. A dataset might also include raw data files such as images or audio. The Modified National Institute of Standards and Technology, or MNIST dataset, is popular for data science. It contains images of handwritten digits and is commonly used to train image processing systems. Now, traditionally, most datasets were private because they contained proprietary or confidential information, such as customer data, pricing data, or other commercially sensitive information. These datasets are typically not shared publicly. Over time, many public and private entities, such as scientific institutions, governments, organizations, and even companies have started making datasets available to the public as open data, providing free information. For example, the United Nations and federal and municipal governments worldwide have published many datasets on their websites covering the economy, society, healthcare, transportation, the environment, and much more. Access to these and other open datasets enables data scientists, researchers, analysts, and others to uncover previously unknown and potentially valuable insights. They are used to create new applications for commercial purposes and the public good. They are also used to carry out further research. Open data has played a significant role in the growth of data science, machine learning, and artificial intelligence. It has allowed practitioners to hone their skills in various data sets. So there are many open data sources on the internet, and you can find a comprehensive list of available data portals worldwide on the Open Knowledge Foundation's datacatalogs.org website. The United Nations, the European Union, and many other governmental and intergovernmental organizations maintain data repositories providing access to a wide range of information. On Kaggle, a popular data science online community, you can find and contribute data sets that might be of general interest. And Google provides a search engine that might help you find data sets that could be of value to you. Now, open data distribution and use might be restricted as defined by certain licensing terms. Without a license for open data distribution, many datasets were shared in the past under open source software licenses. These licenses were not designed to cover specific considerations related to the distribution and use of datasets. So, to address this issue, the Linux Foundation created the Community Data License Agreement, or CDLA. Two licenses were initially created for sharing data: the CDLA Sharing and CDLA Permissive. The CDLA Sharing license grants you permission to use and modify the data. The license stipulates that if you publish your modified version of the data, you must do so under the same license terms as the original data. The CDLA Permissive license also grants you permission to use and modify the data. However, you are not required to share changes to the data. Now note that neither license imposes any restrictions on results you might derive by using the data, which is important in data science. Let's say, for example, that you are building a model that performs a prediction. If you are training the model using CDLA licensed datasets, you are under no obligation to share the model or to share it under a specific license if you choose to share it. In this video, you learned that open data is fundamental to data science. Community Data License Agreement makes it easier to share open data. And open datasets might not meet enterprise requirements due to the impact they might have on the business. Welcome to Sharing Enterprise Data Data Asset Exchange. After watching this video, you will be able to navigate around IBM's Open Data Repository, the Data Asset Exchange, explore open datasets on the Data Asset Exchange, and identify the notebook associated with a dataset in Watson Studio. Now, there are many open datasets available to the public, but it can be difficult to find datasets that are both high quality and have clearly defined license and usage terms. To help solve this challenge, IBM created the Data Asset Exchange, or DAX. DAX provides a curated collection of open datasets, both from IBM research and trusted third-party sources. These datasets are ready for use in enterprise applications with a wide variety of application types, including images, video, text, and audio. DAX aims to foster data sharing and collaboration by keeping datasets available under a Community Data License Agreement, or CDLA. DAX makes it easier for developers to get started with datasets because it provides a single place to access unique, high-quality datasets from trusted sources like IBM Research. It also provides tutorial notebooks that walk through the basics of data cleaning, pre-processing, and exploratory analysis. Certain datasets include advanced notebooks that explain how to perform more complex tasks like creating charts, training machine learning models, integrating deep learning via the Model Asset Exchange, and running statistical analysis and time series analysis. The Data Asset Exchange and the Model Asset Exchange are both available on the IBM developer website. With these resources, developers can create end-to-end analytic and machine learning workflows and consume open data and models with confidence under clearly defined license terms. In the Data Asset Exchange, multiple open datasets are available for you to explore. Let's say you found a dataset that might be very interesting to you, the NOAA Weather Data JFK Airport dataset, which contains data from a weather station at the John F. Kennedy Airport in New York. On this dataset page, you can click Get this dataset to download the NOAA dataset from the cloud storage, run Dataset Notebooks to access the notebooks associated with the dataset in Watson, and preview the data and notebooks to explore DAX metadata, glossary, and the notebook. Now, most datasets on DAX are complemented by one or more notebooks. Click Assets to view all the Jupyter notebooks and data available. You can click the source code to view all the notebooks associated with your NOAA project. You can execute all the notebooks in Watson Studio to perform data cleaning, pre-processing, and exploratory analysis. If you are already familiar with opening the notebooks in Watson Studio, you can log into your IBM Cloud account, create a project, and load all the notebooks into the project. Datasets on DAX also consist of one or more data files. Click the Data option to view the data files available in your project. In this video, you learned that the IBM Data Asset Exchange, or DAX, site contains high-quality open datasets. DAX open datasets include tutorial notebooks that provide basic and advanced walkthroughs for developers. DAX and Max are available on the IBM developer website. You can get, run, and preview datasets and notebooks on DAX. And DAX notebooks are opened in Watson Studio. Welcome to Machine Learning Models, learning from models to make predictions. After watching this video, you will be able to define a machine learning model, describe the different learning model types, and describe how to use a learning model to solve a problem. Now, data contains a wealth of information that can be used to solve certain types of problems. Traditional data analysis approaches can be a person manually inspecting the data or a specialized computer program that automates the human analysis. These approaches reach their limits due to the amount of data to be analyzed or the complexity of the problem. Machine learning, or ML, uses algorithms, also known as models, to identify patterns in the data. The process by which the model learns these patterns from data is called model training. So once a model is trained, it can then be used to make predictions. When the model is presented with new data, it tries to make predictions or decisions based on the patterns it has learned from past data. Machine learning models can be divided into three basic classes: supervised learning, unsupervised learning, and reinforcement learning. The most commonly used type of machine learning is supervised learning. In supervised learning, a human provides input data and correct outputs. The model tries to identify relationships and dependencies between the input data and the correct output. This type of learning comprises two types of models: regression and classification. Regression models are used to predict a numeric or real value. For example, if information is given about past home sales, such as geographic location, size, number of bedrooms, and sales price, you can train a model to predict the estimated sales price for other homes with similar characteristics. Classification models are used to predict whether some information or data belongs to a category or class. For example, for a set of emails, along with a designation, you can classify whether they are to be considered as spam or not, and so you can train an algorithm to identify unsolicited emails. In unsupervised learning, the data is not labeled by a human. The models must analyze the data and try to identify patterns and structure within the data based on its characteristics. Clustering is an example of this learning style. Clustering models are used to divide each record of a dataset into one of a similar group. An example of a clustering model could be providing purchase recommendations for an e-commerce store based on past shopping behavior and the content of a shopping basket. Another example is anomaly detection that identifies outliers in a dataset, such as fraudulent credit card transactions or suspicious online login attempts. And the third type of learning, reinforcement learning, is loosely based on the way human beings and other organisms learn. So think about a mouse in a maze. If the mouse gets to the end of the maze, it gets a piece of cheese. This is the reward for completing a task. The mouse learns through trial and error how to get through the maze to get as much cheese as it can. In a similar way, a reinforcement learning model learns the best set of actions to take, given its current environment, to get the most rewards over time. This type of learning has recently been very successful in beating the best human players in games such as Go, chess, and popular strategy video games. Deep learning is a specialized type of machine learning. It refers to a general set of models and techniques that loosely emulate the way the human brain solves a wide range of problems. It is commonly used to analyze natural language, both spoken and text, images, audio, and video to forecast time series data, and much more. Deep learning has recently been very successful in these and other areas, and hence is becoming an increasingly popular and important tool for data science. It requires large datasets of labeled data to train a model, is compute-intensive, and usually requires special-purpose hardware to achieve acceptable training times. Now, you can build a custom deep learning model from scratch or use pre-trained models from public model repositories. Deep learning models are implemented using popular frameworks such as TensorFlow, PyTorch, and Keras. The learning frameworks provide a Python API, and many support other programming languages such as C++ and JavaScript. You can download pre-trained state-of-the-art models from repositories that are commonly referred to as model zoos. Popular model zoos include those provided by TensorFlow, PyTorch, Keras, and ONNX. Models are also published by academic and commercial research groups. Let's briefly outline the high-level tasks involved in building a model using an example. Assume you want to enable an application to identify objects in images by training a deep learning model. First, you collect and prepare data that will be used to train a model. Data preparation can be a time-consuming and labor-intensive process. In order to train a model to detect objects in images, you need to label the raw training data. For example, you can draw bounding boxes around objects and label them. Next, you build a model from scratch, or select an existing model that might be well-suited to the task from a public or private resource. You can then train the model on your prepared data. During training, your model learns from the labeled data how to identify objects that are depicted in an image. And once training has commenced, you analyze the training results and repeat the process until the trained model performance meets your requirements. When the trained model performs as desired, you deploy it to make it available to your applications. In this video, you learned that machine learning, or ML, uses algorithms, also known as models, to identify patterns in the data. The process by which the model learns data patterns is called model training. Types of ML are supervised, unsupervised, and reinforcement. Supervised learning comprises two types of models: regression and classification. And deep learning refers to a general set of models and techniques that loosely emulate the way the human brain solves a wide range of problems. Welcome to the Model Asset Exchange. After watching this video, you will be able to navigate the Model Asset Exchange from IBM and explain how deep learning model serving detects images. The Model Asset Exchange, or MAX, on the IBM Developer Platform is a free open source resource for deep learning models. The tasks needed to train a model from scratch require a large amount of data, labor, time, and resources. And because of this, time to value can be quite long. To reduce time to value, consider taking advantage of pre-trained models for certain types of problems. These pre-trained models can be ready to use right away, or they might take less time to train. Models are created by running data through a model using compute resources and domain expertise. After research, evaluation, test, train, and validate steps are complete, you will have a validated model. The Model Asset Exchange is a free open source repository for ready-to-use and customizable deep learning microservices. These microservices are configured to use pre-trained or custom trainable deep learning models to solve common business problems. These models have been fully tested and can be quickly deployed in local and cloud environments. All models in MAX are available under permissive open source licenses, making it easier to use them for personal and commercial purposes, which reduces the risk of legal liabilities. On MAX, you can find models for a variety of domains, including object detection, image, audio, video, and text classification, named entity recognition, image-to-text translation, human pose detection, and more. So let's look at the components of a typical model-serving microservice. Each microservice includes a pre-trained deep learning model, code that pre-processes the input before it is analyzed by the model, code that post-processes the model output, and a standardized public API that makes the service's functionality available to applications. Model-serving microservices are created by running inputs through a validated model and then applying the output to a REST API. After implementing package, document, and test steps are complete, you will have a model-serving microservice that can be sent to a local machine or a private, hybrid, or public cloud. Max model-serving microservices are built and distributed as open-source Docker images. Docker is a container platform that makes it easy to build and deploy applications. The Docker image source is published on GitHub and can be downloaded and customized for use in personal and commercial environments. Use the Kubernetes open source system to automate the deployment, scaling, and management of these Docker images. Red Hat OpenShift is a popular enterprise-grade Kubernetes platform. It is available on IBM Cloud, Google Cloud Platform, Amazon Web Services, and Microsoft Azure. In this video, you learned that the Model Asset Exchange is a free open-source repository for ready-to-use and customizable deep learning microservices. To reduce time to value, consider taking advantage of pre-trained models for certain types of problems. Max model-serving microservices are built and distributed on GitHub as open-source Docker images. Red Hat OpenShift is a Kubernetes platform used to automate deployment, scaling, and management of microservices. Welcome to Introduction to Jupyter Notebooks. After watching this video, you will be able to define a Jupyter Notebook, explain how to use Jupyter Lab, and describe how to use the notebooks in Jupyter Lab. Jupyter Notebooks originated as IPython, originally developed for Python programming. Later, when it started supporting additional languages, it was renamed Jupyter, which stands for Julia, Python, and R. However, now it supports many other languages. A Jupyter Notebook is a browser-based application that allows you to create and share documents containing code, equations, visualizations, narrative text links, and more. It is like a scientist's lab notebook, where a scientist records all steps to perform their experiments and the results they can reproduce. In the same way, a Jupyter Notebook allows a data scientist to record their data experiments and results that others can reuse. Now, a Jupyter Notebook file allows you to combine descriptive text, code blocks, and code output in a single file. When you run the code, it generates the output, including plots and tables, within the notebook file. And you can then export the notebook to a PDF or HTML file format that can then be shared with anyone. Next, let's learn about Jupyter Lab. Jupyter Lab is a browser-based application that allows you to access multiple Jupyter Notebook files, other code, and data files. In addition, it extends the functionalities of Jupyter Notebooks by enabling you to work with multiple notebooks, text editors, terminals, and custom components in a flexible, integrated, and extensible manner. It is compatible with several file formats like CSV, JSON, PDF, Vega, and so on. And it is also an open source. Jupyter Notebooks can be used with cloud-based services like IBM and Google Colab. They don't require any installation on your local machine. They give you access to the Jupyter Notebook environment and allow you to import and export notebooks using the standard IPython notebook file format. Also, these services support the Python language and other languages as well. Jupyter Notebooks can be installed via the command line using the pip install function. It can also be downloaded locally on your laptop through the Anaconda platform from anaconda.com. Anaconda is one of the popular distributions which includes Jupyter and Jupyter Lab. So for this course, you have access to a hosted version of Jupyter Lab in Skills Network Labs. so you do not require any installations on your own device to complete the hands-on labs. As shown here, you will see a screen that will launch the Jupyter Lab in the virtual environment. Simply click the Open Tool tab. In this video, you learned that Jupyter Notebooks are used in data science for recording experiments and projects. Jupyter Lab is compatible with many files and data science languages. And there are different ways to install and use Jupyter Notebooks. Welcome to Getting Started with Jupyter. After watching this video, you will be able to describe how to run, insert, and delete a cell in a notebook, work with multiple notebooks, present the notebook, and shut down the notebook session. In the lab session of this module, you can launch a notebook using the Skills Network virtual environment. After selecting the checkbox, click the Open Tool tab, and the environment will open the Jupyter Lab. Here you see the open notebook. On opening the notebook, you can change the name of the notebook. Click File, then click Rename Notebook to give the required name, and you can now start working on your new notebook. In the new notebook, print Hello World. Then, click the Run button to show that the environment is giving the correct output. On the main menu bar at the top, click Run. In the drop-down menu, click Run Selected Cells to run the current highlighted cells. Alternatively, you can use a shortcut by pressing Shift+Enter. In case you have multiple code cells, click Run All Cells to run the code in all the cells. You can add code by inserting a new cell. To add a new cell, simply click the plus symbol in the toolbar. You can also delete a cell. Highlight the cell and on the main menu bar, click Edit and then click Delete Cells. Alternatively, you can use a shortcut by pressing D twice on the highlighted cell. And you can also move the cells up or down as required. So now you have learned to work with a single notebook. Next, let's learn how to work with multiple notebooks. Click the plus button on the toolbar and select the file you want to open. Another notebook will open. Alternatively, you can click File on the menu bar and click Open a New Launcher or Open a New Notebook. And once you open the new file, you can move them around. For example, as shown, you can place the notebooks side by side. On one notebook, you can assign variable 1 to the number 1 and variable 2 to the number 2. And then you can print the result of adding the numbers 1 and 2. As a data scientist, it is important to communicate your results. Jupyter supports presenting results directly from the notebooks. You can create a markdown to add titles and text descriptions to help with the flow of the presentation. To add Markdown, click Code and select Markdown. You can create line plots and convert each cell and output into a slide or subslide in the form of a presentation. The slides functionality in Jupyter allows you to deliver code, visualization, text, and outputs of the executed code as part of a project. Now, when you have completed working with your notebook or notebooks, you can shut them down. Shutting down notebooks release their memory. Click the stop icon on the sidebar. It is the second icon from the top. You can terminate all sessions at once or shut them down individually. And after you shut down the notebook session, you will see No Kernel at the top right. This confirms it is no longer active and you can now close the tabs. In this video, you learned how to run, delete, and insert a code cell, run multiple notebooks at the same time, present a notebook using a combination of Markdown and code cells, and shut down your notebook sessions after you have completed your work. Welcome to Jupyter Kernels. After watching this video, you will be able to define a kernel and describe how to work with kernels. A notebook kernel is a computational engine that executes the code contained in a notebook file. Jupyter kernels for many languages exist, and we will explore some that are relevant in data science. So, when a notebook document opens, the related kernel launches automatically. When the notebook is executed, the kernel performs the computation and produces the results. Now, depending on your settings, you may need to install other notebook languages in your Jupyter environment. In the Skills Network Lab environment, a few languages have been pre-installed for you, and the first one is the Python kernel. When you launch a notebook, pick the language you are interested in for your data science project. The Python kernel allows you to run Python cells. You can run the Python script in the cells to produce an output. The top right corner of the notebook shows the name of the kernel, and here it shows the Python kernel. You do have the option to run other kernels. The Skills Network Virtual Jupyter environment has Apache, Julia, R, and Swift. You can use any language to execute your code, either by selecting the kernel on the launch page or clicking the top right icon and selecting the kernel from the drop-down menu. If running the kernel on your local machine, you will need to manually install the languages through your command line interface or CLI. In this video, you learned that the kernel acts like a computational engine and executes the code in a notebook file. Jupyter Notebook supports different languages, and you can switch to a different kernel as per your requirement. Welcome to Jupyter Architecture. After watching this video, you will be able to describe the basic Jupyter architecture and explain Jupyter architecture for conversion to a file format. Jupyter architecture implements a two-process model with a kernel and a client. The client is the interface offering the user the ability to send code to the kernel. It is the browser in a Jupyter notebook. The kernel executes the code and returns the result to the client for display. Jupyter notebooks represent your code, metadata, contents, and outputs. When you save the notebook, it is sent from your browser to the notebook server. It saves the notebook file on a disk as a JSON file with a .ipynb extension. The notebook server is responsible for saving and loading the notebooks, and the kernel executes the cells of code contained in the notebook when the user runs them. The Jupyter architecture uses the NB-convert tool to convert files to other formats. For example, if we want to convert a notebook file into an HTML file, the notebook is first modified by a preprocessor, then an exporter converts the notebook to the new file format. Finally, a post-processor will work on the exported file to give the final output. After conversion, on giving the URL of the file, the HTML file displays. In this video, you learned that Jupyter implements a two-process model with a kernel and a client. The notebook server is responsible for saving and loading the notebooks. The kernel executes the cells of code contained in the notebook, and the Jupyter architecture uses the NB-convert tool to convert files to other formats. Welcome to additional Anaconda Jupyter environments. After watching this video, you will be able to describe Anaconda and its data science features, describe Anaconda Jupyter environments, and identify tools in Anaconda Jupyter environments. Computational notebooks combine code, computational output, explanatory text, and multimedia resources into a single document. Jupyter Notebook is a popular type of computational notebook because it supports dozens of programming languages. Jupyter Lab and VS Code are popular environments for creating and modifying Jupyter notebooks on a local device. Jupyter Lab is an open-source, web-based application based on Jupyter Notebook. You can create code, interactive visualizations, text, and equations just like with Jupyter Notebook. Jupyter Lab includes expanded features with some of Anaconda's most extensive pre-installed Python libraries, including NumPy, Pandas, and Matplotlib. Anaconda is a free and open source distributor for Python and R, the top languages used in data science and machine learning. Anaconda has 1,500 plus libraries. It is free to install and has free community support for any users who need help with Python. The downloadable Anaconda Navigator graphical user interface allows users to install new packages on their local device without using a command line interface or CLI. You can download Anaconda Navigator from the given URL. So here's the homepage of the Anaconda Navigator. To launch Jupyter Lab, click Launch in the Jupyter Lab box. If the Launch button is missing, click Install first and then click Launch. To start with the Jupyter Notebook, type Jupyter Notebook Anaconda 3 in the search bar and press Enter. The Jupyter Lab dashboard opens in the browser on the local host. It is specifically designed to manage Jupyter Notebooks. To create a new Jupyter Notebook, click New and select Python 3. This opens a new notebook in a new tab. Now you will see the URL, which shows the file name and the kernel. It also shows the last checkpoint. Let's rename your notebook by clicking Untitled. Type a name for the notebook and click Rename. And next, you will review two main cell types, Code and Markdown. In the drop-down menu, select Code. A code cell contains code to be executed in the kernel and displays its output. To execute the cell, click Run. Now, alternatively, in the drop-down menu, select Markdown. A Markdown cell contains rich text and displays its output in place when it executes. To download a notebook, go to File and click Download As, and you will see several download options. You can select the option that you want. VS Code is a free open-source code editor for debugging and task-running operations. VS Code works on Linux, Windows, and Mac OS. It supports multiple languages, syntax highlighting, auto-indentation, and more. VS Code is one of the most popular development environment tools. If you prefer to install VS Code separately without using Anaconda Navigator, you can go to code.visualstudio.com, click the download option that applies to your device, and then follow the install instructions. A separate installation of VS Code will work the same as in Anaconda Navigator, but it will not configure for Anaconda, Python, or Jupyter notebooks. To open VS Code using Anaconda Navigator, open Anaconda Navigator, find the VS Code application, and click Launch. Once installed, you will see the Get Started screen. Now, you do need to install a few extensions to execute Python code in VS Code. First, click Extensions or use Ctrl+Shift+X keys to open extensions. Then search for Python. All the extensions related to Python will appear. Once you install the extensions, click File. Then select New File. In New File, select Jupyter Notebook. The notebook will look like this. Notice that the kernel is Python. Write your code and then execute it using the Run icon. You will get a confirmation that your code has been executed successfully. And finally, navigate to File and select Save. In this video, you learned that Jupyter is a popular computational notebook tool because it supports dozens of programming languages. The Anaconda Navigator GUI can launch multiple applications on a local device. Jupyter environments in the Anaconda Navigator include Jupyter Lab and VS Code. And you can download Jupyter environments separately from the Anaconda Navigator, but they may not be configured properly. Welcome to Additional Cloud-Based Jupyter Environments. After watching this video, you will be able to describe cloud-based Jupyter environments and their data science features, navigate cloud-based Jupyter environments, and identify tools in cloud-based environments. Computational notebooks combine code, computational output, explanatory text, and multimedia resources in a single document. Jupyter Notebook is a popular type of computational notebook because it supports dozens of programming languages. Popular cloud-based environments used to create and modify Jupyter Notebooks include Jupyter Lite and Google Colaboratory. Jupyter Lite is a lightweight tool built from Jupyter Lab components that executes entirely in the browser. Jupyter Lite does not require a dedicated Jupyter server. Only a web server is required, which means you can deploy Jupyter Lite as a static website. We can also use it to create interactive graphics and visualizations because it supports many visualization libraries like Altair, Plotly, and IBM widgets. Since Jupyter Lite is a distribution of Jupyter Lab, it includes the latest improvements and features. To launch Jupyter Lite, open a browser and type jupyter.org/try-jupyter/lab in the URL field. Then press Enter. Jupyter Lite will appear, and next click Python Pyodide. Here is a view of a Jupyter Lite notebook. We know this is a Jupyter Lite notebook because we see the kernel is Python Pyodide. This kernel allows installing and running Python packages in a browser. You will notice different kernels depending on the type of Jupyter environment you use. And for cloud-based Jupyter environments, Python Pyodide and Python Pyolite are common kernels. Now, the default kernel for Jupyter Lite is Pyolite. Pyolite is a Python kernel based on Pyodine. Pyolite runs in the background so that intensive computations can execute quickly. Other kernels can also be used with Jupyter Lite. Google Colaboratory or Google Colab is a free Jupyter Notebook environment that runs entirely in the cloud. Google Colab Jupyter Notebooks execute on a browser, and Google Colab projects are stored on Google Drive and GitHub. You can upload and share notebooks without setup and installation. You can also clone projects from GitHub and execute them in Google Colab. Most machine learning and visualization libraries are pre-installed, like scikit-learn and matplotlib. And with Google Colab, you can develop many trending data science applications on the fly, which is to say, quickly without a lot of setup or preparation. To open the Colab notebook, open Google Drive and click New. To explore Google Colab from the Google Drive menu, select More. Then select Google Colaboratory. The Google Colab notebook will appear. In the notebook, write the code in the Code section, and then to execute the code, click the Run icon. To add more code or text cells, you need to click plus code and plus text. Here, text cells are used to write rich text, or you can set these cells as markdown cells. In this video, you learned that Jupyter is a popular computational notebook tool because it supports dozens of programming languages. The Anaconda Navigator GUI can launch multiple applications. Additional open-source Jupyter environments include the following: Jupyter Lab, Jupyter Lite, VS Code, and Google Colaboratory. And Jupyter Lite is a browser-based tool. Welcome to Introduction to R and RStudio. After watching this video, you will be able to explain what is R, list R capabilities, describe the RStudio environment, and list the R libraries for data science. R is a statistical programming language. It is a powerful tool for data processing and manipulation, statistical inference, data analysis, and machine learning algorithm. Based on a 2017 analysis, it was found that R is used most by academics, healthcare, and the government. R supports importing data from different sources, like flat files, databases, web, and statistical software such as SPSS and Stata. R is a preferred language for some data scientists because R functions are easy to use. It is also known for producing great visualizations and contains packages to handle data analysis without the need to install additional libraries. A popular integrated development environment for developing and running the R language source code and programs is RStudio. It improves and increases productivity with the R language. RStudio includes a syntax highlighting editor that supports direct code execution and a place where you can keep a record of your work, a console for typing R commands, a workspace and history tab that shows the list of R objects you created during your R session and the history of all previous commands, and finally, files, plots, packages, and help tabs. The Files tab shows files in your working directory. The Plots tab displays the history of plots you have created. You can also export plots to PDF or image files. The Packages tab displays external R packages available on your local computer. And the Help tab provides help on R resources, RStudio support, packages, and much more. If R is your tool of choice for data science, here are some popular R libraries available in the data science community. dplyr for manipulating data, stringer for manipulating strings, ggplot for visualizing data, and caret for machine learning. To get you up and learning quickly, we have provided you with an RStudio virtual environment as part of the Skills Network Labs. This virtual lab environment is designed to assist you to easily practice what you learn in the course and skip the need to create an account or download or install anything. In this video, you learned the capabilities of R and its uses in data science, the RStudio interface for running R codes, and popular R packages for data science. Welcome to Plotting in RStudio. After watching this video, you will be able to list the R data visualization packages, use the inbuilt rplot function, use the R ggplot library to add functions and arguments to the plot, and add titles and names to the plot. With the influx of data, one of your many jobs as data scientists is to produce insights using visualizations. R has different packages for data visualization that you can use based on your requirement. To install these packages in your R environment, use the install.packages and the package name command. Examples of R packages include the following. ggplot is used for data visualizations such as histograms, bar charts, scatter plots, and so on. It allows adding layers and components to a single visualization. Plotly is used for web-based data visualizations that can be displayed or saved as individual HTML files. Lattice is used to implement complex multivariable datasets. It is a high-level data visualization library that can handle graphics without customizations. And Leaflet is used for creating interactive plots. R has inbuilt functions to create plots and visualization. For example, you can create a plot using the definition shown here. The plot function returns a scatter plot of the values versus the index. You can also add lines to the function and a title to make the visualization easier to read and understand. To add a line, you specify the type, and to add a title, you specify the title function. And now in the plot, you have added a line and a title. You can create informative visualizations using the ggplot library of R. It can handle complex requests by adding layers to plots using different functions and arguments. For example, to create a scatter plot, let's use the inbuilt dataset mtcars. You will first read the ggplot library into the memory using the library function. Next, use the ggplot function on the data frame mtcars. Specify the x-axis as miles per gallon and the y-axis as weight. Then add the geomePoint function to specify a scatter plot, otherwise it will return an empty plot. The output will be an easier-to-read plot. In addition, you can add titles and change the axis name by using the ggTitle argument and the labs argument to specify appropriate names for both axes. The result will be a graph with meaningful titles. Now, in the lab, you will recreate the graphics with ggplot and the extension library called ggalley. ggalley extends ggplot by adding several functions to reduce the complexity of combining geometric objects with transformed data. In this video, you learned about popular data visualization packages in R, plotting with the inbuilt rplot function, plotting with ggplot, and adding titles and changing the axis name using the ggtitle and labs function. In this video, you will get an overview of Git and GitHub, which are popular environments among developers and data scientists for performing version control of source code files and projects, and collaborating with others. You can't talk about Git and GitHub without a basic understanding of what version control is. A version control system allows you to keep track of changes to your documents. This makes it easy for you to recover older versions of your document if you make a mistake, and it makes collaboration with others much easier. Here is an example to illustrate how version control works. Let's say you've got a shopping list, and you want your roommates to confirm the things you need and add additional items. Without version control, you've got a big mess to clean up before you can go shopping. With version control, you know exactly what you need after everyone has contributed their ideas. Git is free and open source software distributed under the GNU General Public License. Git is a distributed version control system, which means that users anywhere in the world can have a copy of your project on their own computer. When they've made changes, they can sync their version to a remote server to share it with you. Git isn't the only version control system out there, but the distributed aspect is one of the main reasons it's become one of the most common version control systems available. Version control systems are widely used for things involving code, but you can also version control images, documents, and any number of file types. You can use Git without a web interface by using your command line interface, but GitHub is one of the most popular web-hosted services for Git repositories. Others include GitLab, Bitbucket, and Beanstalk. There are a few basic terms that you will need to know before you can get started. The SSH protocol is a method for secure remote login from one computer to another. A repository contains your project folders that are set up for version control. A fork is a copy of a repository. A pull request is the way you request that someone reviews and approves your changes before they become final. A working directory contains the files and subdirectories on your computer that are associated with a Git repository. There are a few basic Git commands that you will always use. When starting out with a new repository, you only need create it once, either locally and then push to GitHub, or by cloning an existing repository by using the command git init. Git add moves changes from the working directory to the staging area. Git status allows you to see the state of your working directory and the staged snapshot of your changes. Git commit takes your staged snapshot of changes and commits them to the project. Git reset undoes changes that you've made to the files in your working directory. Git log enables you to browse previous changes to a project. Git branch lets you create an isolated environment within your repository to make changes. Git checkout lets you see and change existing branches. Git merge lets you put everything back together again. To learn how to use Git effectively and begin collaborating with data scientists around the world, you will need to learn the essential commands. Luckily for us, GitHub has amazing resources available to help you get started. Go to try.github.io to download the cheat sheets and run through the tutorials. In the following modules, we'll give you a crash course on setting up your local environment and getting started on a project. Welcome to Introduction to GitHub. After watching this video, you will be able to describe the purpose of source repositories and explain how GitHub satisfies the needs of a source repository. Linux development in the early 2000s was managed under a free-to-use system known as BitKeeper. In 2005, BitKeeper changed to a for-free system, which was problematic for Linux developers for many reasons. Linus Torvalds led a team to develop a replacement source version control system. The project ran in a short time frame, and the key characteristics were defined by a small group. These include strong support for nonlinear development. Linux patches were then arriving at a rate of 6.7 patches per second. Distributed development. Each developer can have a local copy of the full development history. Compatibility with existing systems and protocols. This was necessary to acknowledge the diversity of the Linux community. Efficient handling of large projects. Cryptographic authentication of history. This makes certain that distributed systems all have identical code updates. Pluggable merge strategies. Many pathways of development can lead to complex integration decisions that might require explicit integration strategies. What is special about the Git repository model? Git is designed as a distributed version control system, primarily focused on tracking source code during development. Contains elements to coordinate among programmers, track changes, and support nonlinear workflows. Created in 2005 by Linus Torvalds for distribution of Linux kernels. Git is a distributed version control system that is used to track changes to content. It serves as a central point for collaboration with a particular focus on agile development methodologies. In a central version control system, every developer needs to check out code from the central system and commit it back into it. As Git is a distributed version control, each developer has a local copy of the full development history, and changes are copied from one such repository to another. Each developer can act as a hub. When Git is used correctly, there is a main branch that corresponds to the deployable code. Teams can continuously integrate changes that are ready to be released and can simultaneously work on separate branches in between releases. Git also allows centralized administration of tasks with access-level controls for each of them. Git can coexist locally, such as through the GitHub desktop client, or it can be used directly through a browser connected to the GitHub web interface. IBM Cloud is based on sound and established open-source tools, including Git repositories, often called repos. GitHub is an online hosting service for Git repositories. GitHub is hosted by a subsidiary of Microsoft. GitHub offers free professional and enterprise accounts. As of August 2019, GitHub had over 100 million repositories. A repository is a data structure for storing documents, including application source code. A repository can track and maintain version control. GitLab is a complete DevOps platform delivered in a single application. GitLab provides access to Git repositories controlled by source code management. With GitLab, developers can collaborate, reviewing code, making comments, and helping to improve each other's code. Work from their own local copy of the code. Branch and merge code when required. Streamline testing and delivery with built-in continuous integration, CI, and continuous delivery, CD. In this video, you learned GitHub is the online hosting service for Git repositories. Repositories store documents, including application source code, and enable contributors to track and maintain version control. What is special about the Git repository model? Git is designed as a distributed version control system, primarily focused on tracking source code during development. Contains elements to coordinate among programmers, track changes, and support nonlinear workflows. Welcome to GitHub Repositories. After watching this video, you will be able to explain how to sign up for a GitHub account, and describe how to create a repository. Signing up for a free personal account on GitHub is quick and easy. Start at the GitHub site, https://github.com. You'll need to choose a username, enter your email address, and select a password. Then click Sign Up for GitHub. Next, you'll have a short test to prove that you're a person. Click Verify and solve the puzzle presented. When you're done, click Join a Free Plan, and then you'll be taken to a screen where you can select the type of account. Most likely, a free personal account is all that you'll want. Choose to set up a personal free account, which is the default. GitHub asks some questions about your work, programming experience, and interests. You can skip these if you want. Finally, you'll have to respond to an email that you receive which proves that you link to GitHub from an account that you access. GitHub provides you with some starting points. You can choose to create a repository or an organization, or you can take the Introduction to GitHub course. Remember, a repository is a data structure for storing documents, including application source code, which tracks and maintains version control. An organization is a collection of user accounts that owns repositories. Organizations have one or more owners who have administrative privileges for the organization. Or you can skip this for now and get straight to work. GitHub provides many resources to help you work efficiently. When you have time, read the GitHub guide. The heart of a Git-based project is the repository. This contains all your code and the related artifacts, including things like a README file to describe the purpose of the project, a license to express the ways in which people can use your code, etc. You can also make your repository private, only available to people with accounts that have permission to see it, or public, searchable and seen by everyone. When you create your repository, you'll notice that it has a number of tabs and is open to the Code tab. Code. This is where all the source files reside. Git was initially created as a source code repository, and now all sorts of files end up in here. If you created a README and/or license, that's all that's here right now. Issues. As you can imagine, you can track and plan with tools such as Issues that lists all open items against your project base. Pull requests. This is part of the mechanism for collaborating with other users. Pull requests define changes that are committed and ready for review before being merged into the main branch. Projects. All the tools for managing, sorting, planning, etc. your various projects. This is the core of the collaborative power of GitHub. Wiki, security, and insights. Often left for more advanced users, these tools provide a communication base to the external user community. Settings. GitHub allows for a lot of personalization, including changing the name of your repository and controlling access. In this video, you learned how to create and verify a GitHub account. Repositories are storage structures that can hold code, track issues, and enable you to collaborate with others. In the previous video, you learned about Git and GitHub. Before you continue with this video, register for a GitHub account and log in. Let us start by creating a new repository. Click Plus, then click New Repository. To create a new repository, you need to provide these details. Give your new repository a name. Optionally, add a description of your repository. Choose the repository visibility, whether you want it to be public or private, and choose the option to initialize this repository with README file. Then click Create Repository. You will now be redirected to the repository you have created. The root folder of your repository is listed by default, and it has just one file, readme.md. Now it's time to edit the README. You can do this in your browser. Just click the pencil to open the online editor, and you can change the text of the README. To save your changes to the repository, you must commit them. After you have made your changes, scroll down to the Commit Changes section. Add a commit message and optionally add a description. Then click Commit Changes. Commit Changes is used to save your changes to the repository. Go back to the home screen by clicking the repository name link. Note that the README file is updated and verify your changes. Let's learn how to create a new file using the built-in web editor provided by GitHub, which runs in the browser. Click Add File, then click Create New File to create the new file. To create a Python file called firstpython.py, first provide the file name. Next, add a comment that describes your code, then add the code. Once finished, commit the change to the repository. You can see that your file is now added to the repository, and the repository listing shows when the file was added or changed. When you need to change the file, you can edit it again. Click the file name, then click the pencil icon, make your edits, and commit the changes. You can also upload a file from your local system into the repository. From the home screen of the repository, click Add File and choose the Upload Files option. Click Choose Your Files and select the files you want to upload from your local system. The file upload process may take a short time, depending on what you are uploading. Once the file finishes uploading, click Commit Changes. The repository now reflects the files that were uploaded. In this video, you learned how to create a repository, edit files, and commit changes using the web interface. Welcome to GitHub Working with Branches. After watching this video, you will be able to define a GitHub branch, create master and child branches, describe how to merge branches, and create a pull request. A branch is a snapshot of your repository to which you can make changes. It is a copy of the master branch and can be used to develop and test workflow changes before merging it into the master branch. In Git and GitHub, there is a main branch called master. It has the deployable code and is the official working version of your project. It is meant to be stable, thus it is advisable not to push any code that has not been tested in the master. If you want to change the code and the workflow in the master branch, you can create a copy of the master branch. This can be the child branch that will be a copy of the workflow. Now, in the child branch, changes and experiments are done. You can build, make edits, and test the changes. And when you are satisfied with them, you can merge them back to the master branch where you can prepare the model for deployment. You can see that all of this is done outside the master branch, and until you merge, changes will not be made to the workflow before you branched. To ensure that changes done by one member do not impede or affect the workflow of other members, multiple branches can be created and merged appropriately with the master after the workflow is properly tested and approved. So, to create branches in GitHub, let's look at the repository. There is currently one branch in the repository. You want to make some changes, but don't want to alter the master in case something goes wrong, so you will create a branch. To do that, you will click the drop-down arrow and create a new branch. Name the new branch Child Branch, and then click Enter. The repository now has two branches, the master and child branches. You can check this by selecting the child branch in the branch selector drop-down list. All the content in the master branch is copied to the child branch. However, you can add files in this child branch without adding any to the master branch. To add a file, ensure the child branch is selected in the branch selector drop-down list. Then click Create New File. In the space provided, name the file testchild.py, and then add a few lines of code. You can print the statement inside the child branch. At the bottom of the screen, you will see a section, Commit New File. Commit messages are important as they help to keep track of the changes made. Add a descriptive commit message for the convenience of the team. Here, you can add create_testchild.py, then click Commit New File, and the file is added to the child branch. You can verify by going to the master branch by clicking Master from the branch selector menu, and you can see that the new file is not added to the master branch. After you have created the new file, test and ensure it is working. You can merge the changes in the child branch to reflect the master branch by creating a pull request or PR. Pull requests show the differences in the content from both branches, and it can notify other team members of the changes and edits to the main branch. Ideally, another team member reviews the changes and approves them to be merged with the master branch. Pull requests are the means of collaboration on GitHub. When you open a pull request, you propose your changes. You can assign team members to review and approve your contribution and merge in the target branch. To open a pull request to see the differences between the branches, click Compare and Pull Request. If you scroll down to the bottom of the screen, you will see the comparison between both branches. It shows one file has changed and the file has 2 additions, the 2 lines you added to the file with 0 deletions. You will now create the pull request. Add the title and an optional comment. Click Create Pull Request. The next screen will show the details of the pull request, and if you are okay with the changes, click Merge Pull Request and then click Confirm. You will get a confirmation that the pull request has been successfully merged, and you can also delete the branch if you no longer need to edit or add new information. Now, the child branch has completely merged with the master branch, and you can check the master branch and verify it contains the testchild.py file. In this video, you learned a branch is a snapshot of your repository to which you can make changes. In the child branch, you can build, make edits, and test the changes, and then you can merge them with the master branch. To ensure that changes done by one member do not impede or affect the workflow of other members, multiple branches can be created and merged with the master. And a pull request is a way to notify other team members of the changes and edits to the main branch. Welcome to Introduction to Watson Studio. After watching this video, you will be able to explain what Watson Studio is for and who uses it, list the components of IBM Cloud Pak for Data, find common resources in Watson Studio and IBM Cloud Pak for Data, and build models and manage services and integrations. Watson Studio is a collaborative platform for the data science community. Data analysts, data scientists, data engineers, developers, and data stewards all use Watson Studio to analyze data and construct models. With Watson Studio, you can create projects to organize data connections, data assets, and Jupyter notebooks. You can upload files to your project, and you can clean and shape the data to refine it for analysis. You can then create and share data visualizations via dashboards without using any coding. Watson Knowledge Catalog provides a secure enterprise catalog management platform to deliver trusted and meaningful data. And Watson Machine Learning offers tools and services to build, train, and deploy machine learning models. Cloud Pak for Data as a Service is a secure, seamless data access and integration platform that enables a single view of the data, no matter how many data sources you are working with. It includes IBM Watson Studio, IBM Watson Knowledge Catalog, and IBM Watson Machine Learning, and more. In IBM Cloud Pak for Data, you can find step-by-step tutorials that show you how to integrate data from multiple sources, build, deploy, test, and more. You can create collaborative data workspaces called projects where your team can perform tasks for data science, data engineering, data curation, or machine learning and AI. And you can read Cloud Pak for Data news and updates. As you scroll down, you will see your work highlights, recent activities, and shortcuts. The Quick Start section has links to get you started, and the navigation menu is on the upper left. In the navigation menu, Projects show you projects and jobs you have created. In Deployments, you can train, deploy, and manage machine learning models in collaborative deployment spaces. In Services, you can view different services associated with your account and explore the catalog. And Gallery shows a collection of datasets, notebooks, industry accelerators, and sample projects. Now, on the Gallery page, you can search for projects and filter your search by clicking All Filters. You can filter by format and topics. You can then explore different project types. And you can also explore the data. Once you select the project, you will see the notebook, when it was last modified, the problem statement, and more. You can add to your project or download the notebook to your system. One of the core services in Cloud Pak for Data, Watson Studio Architecture, is centered around the project. To create a project, select Work with Data from the Cloud Pak for Data homepage. The Create a Project pop-up will appear with options to create an empty project or create a project from a sample or file. Now, when you click Create an Empty Project, this page loads. Here, you can manage all your projects. Use the Context Information and Actions menu from anywhere in the project to view project information or load data files as assets. The RStudio Integrated Development Environment, or IDE, is included with IBM Watson Studio, so you can use R notebooks and scripts in your projects. Launch RStudio from the Launch IDE menu after you create a project. The Overview page keeps you up to date with recent assets you created, the resource usage of the project, a README for your project description, and a project history. To find project assets, click the Assets tab. The New Assets button lets you use data and tools to create analytical assets like flows, visualizations, experiments, or notebooks. And the Import Asset button lets you import assets. A job is a way of running assets such as data refinery flows or notebooks in a project. Under the Jobs tab, you can run a job immediately or schedule a job. You can manage your projects under the Manage tab. There, you can control access with user groups, define environments and monitor active runtimes, see resource usage, and tools and processing power using services and integrations. In Service and Integration, you can associate IBM Cloud Services with your project to add tools, environments, and capabilities. And you can also use third-party integrations so your project can interact with external tools. For example, you can integrate with a Git repository to export the project, work with documents and notebooks in Jupyter Lab, or back up the project. From the Asset tab, you can use graphical builders, like Dashboards Editor, to create a shareable visualization in the dashboard, or Data Refinery to create flows to refine data. Decision Optimization has the Decision Optimization Model Builder to solve scenarios. And with SPSS Modeler, you can quickly develop predictive models and deploy them into business operations to improve decision-making. The new asset tool type options also include code editors, which provides a Jupyter Notebook editor where you can analyze data or build models. A Jupyter Notebook is a web-based environment for interactive computing. You can use notebooks to run small pieces of code that process your data, and you can immediately view the results of your computation. Now, this Jupyter Notebook editor is largely used for interactive, exploratory data analysis programming and data visualization. You should use it if you are new to Jupyter Notebooks. In this video, you learned that Watson Studio is a helpful tool for analyzing and viewing data, cleaning and shaping data, embedding data into streams, and creating, training, and deploying. Learning Watson Studio promotes career growth. Learning Watson Studio is easy and requires no special skills. And Watson Studio offers many available resources. Welcome to Jupyter Notebooks in Watson Studio, Part 1. After watching this video, you will be able to create a Jupyter Notebook and load a data file, share a Jupyter Notebook with others, and create a job and schedule it to run. In the previous video, you learned how to create a project. Once created, you will see this page. Click New Asset to add or create a new notebook. Under Tool Type, select Code Editors, and then select Jupyter Notebook Editor to create a new notebook. On the New Notebook page, you can create a blank notebook, upload a notebook file from your file system, or upload a notebook file from a URL. In this video, we will create a blank notebook. First, provide a notebook name and description, and you need to specify the runtime environment for the language you want to use. For example, Python, R, or Scala. Then click Create to create a notebook. Now, after you create a notebook, you will upload the data. Make sure data you load and the code commands you use to analyze that data both match the kernel runtime language you selected when you created your notebook. To upload the data, click Find and Add Data. In the Data pane, browse for the files or drag them onto the pane. You must stay on the page until the upload is complete. And you also have the option to cancel an ongoing upload process if need be. Now the data is available to work on. Click Insert Code and select Pandas data frame. It is a best practice to insert a cell at the top of the Jupyter Notebook using the Insert Cell Above option from the Insert tab. Now a cell is added. Now change the cell type to Markdown so the cell will not be treated as code. In the Markdown cell, describe what the notebook does and run it. You're now ready to run the notebook. The inserted code loads the dataset into a data frame. Run the code cell to display the first 5 rows of the dataset. From the File tab, select the Same Version option to save the latest changes in the notebook. Then click the project name to return to the project home page. Now, back on the project home page, under the Assets tab, select the Source Code tab in the left navigation pane. You'll find the notebook on which you have recently worked. Click to open it. The notebook will open in a read-only mode. To edit it, click the pencil icon in the Notebook action bar. Now, when the View Notebook Info icon is selected, under the General tab, you can change the name and description of your notebook and see the last editor, last modified date, and the creation date. On the Environment tab, you can see the environment template used to open the notebook, change the template, view the environment details, and check the runtime status. You can also create a URL to share the notebook on social media or with people outside of Watson Studio. The URL shows a read-only view of the notebook. Anyone who has the URL can view or download the notebook. Click the Share icon in the Notebook action bar to see sharing options in a pop-up window. So, if you want to share a read-only version of the notebook, in the dialog box, enable the option Share with anyone who has a link. Now, you can select how much of the content you'd like to share by selecting Only Text and Output or All Content excluding sensitive code cells in the sharing options. You can then share the notebook either through a link or on social media. The Jobs feature provides an efficient way to run, schedule, and monitor jobs in a Watson Studio project. Click the Create a Job icon from the Notebook action bar and click Create a Job. In the Define Details page, enter the job name and description and then click Next. In the Configure page, enter all the required details and then click Next. You can also add a one-time or repeat schedule on the Schedule page. If you define a start day and time without selecting Repeat, the job will run exactly once on the specified day and time. Select the start day and time and then click Next. Also, if you require a notification for this job, enable the notification option and then click Next. Now review the job details and click Create. To view the job you created, go to the Jobs tab, and from here you can edit and delete the job. In this video, you learned that you can add or create a new notebook by clicking New Asset on the project homepage under the Assets tab. You can share your notebook without sharing the sensitive cells. Jobs are created and scheduled from the Create a Job icon in the Notebook action bar, and jobs can be viewed, edited, or deleted on the project homepage under the Jobs tab. Welcome to Jupyter Notebooks in Watson Studio, Part 2. After watching this video, you will be able to check the Jupyter Notebook runtime environment, use different types of Jupyter Notebook templates, and change the kernel within a Jupyter Notebook. So, you have learned how to create a Jupyter Notebook. Now you will learn to manage the environment. Go to the Data Science Project homepage and click the Manage tab, and then, in the left pane, click Environments. If your notebook is executing, you will be able to see the active runtime environment. Note that you can execute your notebook to see the active runtime if it is not visible. To see the available runtime environments, click Templates. In the template name list, you can explore available runtime environment templates. Select any template as your active runtime environment. Let's select the RStudio environment. Now, on selecting the template, you will see the summary of the template and its software configuration details. To create a new template, go back to the Templates page and click New Template. Enter the environment name, its description, and configuration. Then, click Create to create the environment. A summary and software configuration details of the new template will be displayed. To change the current runtime to the newly created template runtime, click the Assets tab, and then select the new notebook you created. If you see the lock icon, unlock it and select the notebook again. Next, select the three dots on the right and click Change Environment. Select the new template environment you created and click Change. In the pop-up, select the kernel from the drop-down option and click Set Kernel. On the top right corner, you will see the new runtime. Now you can drag and drop any CSV file to upload, and then click Insert to Code to include the code into the notebook. To execute the notebook, click Run, and you will see that the output is now using the new runtime environment. In this video, you learned that Jupyter Notebook runtime environments and templates can be found on the Environments tab in the home page, and you can create and change new Jupyter Notebook templates. Welcome to linking GitHub to Watson Studio. After watching this video, you will be able to describe how to connect a Watson Studio account with GitHub and describe how to publish Watson Studio notebooks on GitHub. You now know how to create a new project and notebook. So let's open your project and find the data science notebook you created in a previous module. To integrate Watson Studio to GitHub, click Manage, then on the left panel under Project, click Service and Integrations. Next, in IBM Services, select Third-Party Integrations and then click Connect Integration. In Connect Integration, to establish the connection, select GitHub and click Next. Click the Personal Access Token hyperlink to create the new access token. Log in to your GitHub account by entering your username and password. Then click Sign In. To create a new personal access token, provide the description of the token, and to define the access for personal tokens, under Select Scopes, select Repo. Next, ensure GIST is selected and click Generate Token. In the Personal Access Token page, copy the generated access token by clicking the Copy icon. Now, go back to the Connect Integration area and add the generated token. Next, you must find the repository URL for the location you want to push the notebook. To get the repository URL from GitHub, ensure you are in the master branch of the repository you want to use. Click Code and copy the URL using the Copy icon. Now go back to the Connect integration area and enter the repository URL where you want to push the notebook. Then click Connect. Once the repository is added, you get a successfully connected message. Now you can go back to the Assets tab and select the notebook you want to push to GitHub. Once the notebook is open, on the top right, select the down arrow and click Publish on GitHub. On the Publish on GitHub page, select all content except hidden code cells, then click Publish. A successful Publish message will pop up with the name of the notebook file and repository. In the GitHub, you can see the notebook datasciencenotebook.ipynb, which confirms that you published your notebook from Watson Studio. In this video, you learned that Watson Studio accounts can be integrated into GitHub, and you can push notebooks from Watson Studio to GitHub.